Okay, this is 5.1. We're going to start to talk about systems of linear equations. And this is the beginning, the very, very beginning of an area of math that is arguably my favorite area, which sounds really nerdy, but that's what it is. And the reason is because it has a combination of being really, really um, elegant and simplistic, but at the same time, it has huge applications. Um, I have I know one teacher at the college at Palm Beach State College. I think he says in his notes that linear algebra, which is what we're just barely stepping into, um, is 75% of what is done in engineering and in finance or stock market research. It's all applications of a field of math that involves solving many equations at one time and linear equations at one time. Uh, you'll often have a scenario where the equations aren't linear, but it becomes so complicated that you try to approximate solutions by making them by making a linear scenario out of it. But I don't want to get too technical with it. But point is that this is a very, very if there's any time to listen and wonder like what's the point of this? Why do I need to learn this? It's at this section because this has a lot of applications. It kind of matures you mathematically a little bit. It gets you to kind of zoom out and think in a bigger picture. At the same time, helping you get specific and solve for x and y and vectors and things like that. So we're skipping chapter 4 and the end of chapter 3 for now. I want to go back to that stuff, but I want to really get into this so that way we can get through chapters 5 and 6, which are all about systems of linear equations and solving them, and then eventually matrices and a little bit of linear algebra. So, um, to start off, we've explored these central objects of investigation, as Wikipedia calls them, and the name of these things are functions. We've explored functions, um, and we've come across a lot of different types of functions. Um, so I have here a set that I've drawn. It's a set of all relations, and remember that not every relation is a function. If some certain relations, at least in the simple examples I gave, may not pass the vertical line test, which really means if you're talking about a set, which is how we can talk about everything in math, um, it's a set of ordered pairs, the first one being x, the second one being y. A function, or what we've been exploring, is not the set of all relations. We've realized that there are certain things out there called relations, but they're not super relevant to talk about all the time because the point of math is to predict, right? And so these things that allow us to predict are called functions. So I'll label that f. The set of functions from a set x to a set y, right? That's we've been exploring a subset of this, and even in that, we talked about domain and range, and this would be the domain with this notation. This would be the codomain. A subset of y would be the range. And even in exploring functions, we were a little bit too zoomed out. We had a big picture idea in chapter 1, and then beginning in chapter 2, we realized that, well, if we really want to solve problems, we can't just talk about functions in general. That gives us an intuition about things, but it doesn't really help us get down and dirty and solve a specific problem. So we started exploring um, some certain types of functions. We explored the polynomials, right? That was what we just covered. That's a P right there, polynomials. And in those polynomials, we had two specific types that we looked at. We looked at the linear functions, and we look at the quadratics, right? And even in that took months, or yeah, a couple months, I guess, to get through just how to solve those and the different techniques involved in solving those. And then in chapter 3, we looked at polynomials in general, and realized that they can get very difficult to solve, even when you just have something as small as degree 5 or 6. They're not solvable at that point in general. You can have certain cases where with something like maybe x to the 5th plus 1 equals 0, that might be solvable, but in general, a quintic polynomial, you can't. So it gets complicated really fast. And this is what we've explored about functions, just this little tiny area. And there's other functions out there that we're skipping over right now. There's the rational functions. And the name even makes sense, rational, because the polynomials behave a lot like the integers do. So the polynomials are like the integers of the function world, and the rational function are involve the division of two polynomials. So, or just like a rational number is a division of two integers. So these functions we'll explore, and they'll have certain patterns in their shape, the graphs. These a rational function will have certain discontinuities. Like something simple might be 1 over x, which is really not that graph. I just drew it so quickly that it's kind of poor. But there's asymptotes and things like that with rational functions. And then there's we'll explore the exponential functions, which are not even in any of these two sets. The exponential functions, I mean, it's kind of arbitrary where I draw it, but exponential, which are things of the form f of x is equal to a to the x. So we saw this a little bit, and we just knew it wasn't a polynomial because you couldn't have x in the exponent. That's what we said on the test or the quiz, whatever it is I gave you. And he said, "Oh, that's definitely not a polynomial." Well, it is not a polynomial, but it's a type of function that we'll eventually learn about, and has applications in talking about things like interest rates and population growth and radioactive decay. It just comes up a lot. And then every function has an inverse, right? Or I'm sorry, not every one-to-one function has an inverse, and we'll learn that exponential functions are one-to-one, and so their inverses are the logarithmic functions. So we'll explore those. So all of these functions that we've been talking about, though, they have one thing in common. And notice how I say one there. I'm kind of hinting at it a little bit in a nerdy way. They have one thing in common. They're all different in how they express this one thing, but it's still one thing. They are all functions of one variable. I mean, that just has to give you a feel for how complicated things get in the real world. I mean, we've spent 6 months, I don't know, since August, starting to talk about this stuff, and the whole time we're talking about something as simple as f of x, one variable. There's a whole nother set, not even that's not even in here in this big set that I've drawn about all the thinking that we've done that involves functions of two variables. So I might have a set somewhere outside of here where I have f of x and y going to a set z. So that might look like something like f of xy is equal to x squared plus 2y or something like that. So now I have a function of two variables, and I'll call the third dependent variable, I'll call that z a lot of times. And that's where you need a 3D plane to graph things, and then you have 3 variables and 4 variables. So I asked what would be a natural next step as we explore functions, and the answer might be Let's talk about functions of two variables. Yeah, we want to do that, but we have to be careful how we tread that ground because that gets really ugly, really complicated, really fast. And I know I keep saying that, but it's true. So you yeah, I even wrote it here. As I've said, things get very complicated very quickly. So here's an example to illustrate what I mean. I have three functions listed here, um, each of three variables, x, y, and z. So x times y times z, z cubed, and 5x minus 2y plus z. This is what we would call a system of equations, right? And I want to look at this versus, let's say, this system here, which I haven't even fully written. I'll say 5x minus y plus z. And let me write a third one. 6x minus 4y minus 2z. Okay? So they both, I guess, look ugly probably to the person first looking at it, but which one looks uglier? My answer would be this one. I have a cube in here. These are multiplying here, and maybe I should add a little something extra. I should square that y just to really bring home the point that this is uglier. This, there's no powers. You might think it looks kind of like a polynomial. It's certainly not a polynomial of one variable, but these are just nicer looking to deal with. This is what we would call a system of nonlinear equations, because in order for something to be linear, as we explored, of one variable, you can't have powers different than one. And really, in order for it to be linear of many variables, the variables can't be multiplying. So these types of systems they're huge. There's so many different scenarios that it's hard to even talk about. There's so many different types of nonlinear things, and they're complicated to solve. Really, yeah. Let me just leave it there. They're complicated to solve. This is a system of linear equations. There's all of power 1. They're all adding. It's a system of linear equations, and linear algebra and matrices all come from trying to solve these things, systems of linear equations. And the reason that I wrote three equations for three different variables is because you need at least as many equations as you have variables in order to find a solution for that problem. By solution, what I mean is, some point, because this is x, y, and z, so I need some point, let's say 3, 4, 5. I mean, that might be the solution, but so what I'm looking for here is I'm looking for an overlap of planes or linear equations, and they're going to it might be the second plane, and then there might be a third plane here, and the overlap would happen at a point. Okay, so that point is the solution. So if we're looking for a solution, meaning I'm looking for x is equal to a number, y is equal to a number, z is equal to a number, there's a very, very systematic way of doing that when your system is linear and you're dealing with linear equations. Nonlinear equations, again, because there's so many different scenarios and just a little tiny change can really change the whole problem, they're very complicated to deal with, and it's not as systematic. In fact, that's still explored, solving nonlinear systems, especially when you talk about something called differential equations, which is beyond this course. But okay, so this is what we want to talk about because this is nicer. So hopefully I didn't babble on too much there. So we want to only talk about linear. Whoops. We want to only talk about linear multivariable equations, and we want to talk about systems of these equations. Because, like I said, you need at least as many equations as you have variables if you really want to find a number for each of those variables. Okay. So, let me stop babbling. We'll do an example. So let's say on page 386 and 387, let's say I'm selling tickets at a computer fair, and I have student tickets, which I'll call X, and I have general admission tickets. Okay. So for now, we'll solve this visually. If I sold 7 tickets, if a total of 7 tickets were purchased, and the cost was $18, how many of each type were purchased? And this is in page 386. So let's write out in Math Talk what it is that it's giving us. So I have the total number of tickets. I need an equation to describe that. Well, I have my student tickets and I have my regular tickets. So if I add those up, I get my total number of tickets. How many did I sell? I sold 7. The cost of the tickets, it's $2 for the student tickets. So how much money do I make? That's this equation. 2 for every student ticket plus $3 for every general admission ticket. And I made a total of $18. So the question is, how many of each type were purchased? How many student tickets were purchased? How many general admission tickets were purchased? So we're going to start out solving this visually, meaning that we graph and we actually see where the lines cross, because that's what you have with systems of linear equations. You have basically lines or planes or linear objects overlapping somehow. So this first graph is going to be at 7, and x is equal to 7. So this is the graph of 1. See, it goes through those two, right? And then this is the graph of 2. It goes through 6, which is right here, and it goes through 7, which is over here. Oh no, I'm sorry. It goes through 9. So let's say 9 is right about there. So that's a little bit of a shallower graph. Okay, this is graph 2. So since both of these things are true at the same time, what I can do is I can draw these two on the same graph and see where they overlap, and that point that they overlap is the point at which both of these are true at the same time. So that will be our solution. So again, 7 and 7. So 0, 7 and 7, 0 give me my first graph. And then 0, 6 and 9, 0 give me my second graph. Okay. This point here is supposed to be 3, 4, which is pretty close. 3, 4. So what does that mean? That means I sold 3 student tickets and I sold 4 general admission tickets. So the point at which they intersect intersect is the solution. And yeah, that would be a point xy is equal to 3 comma 4. I guess we could write it like that. So, is it possible to have exactly two solutions? What I'm trying to lead into is, what are the different ways, as we visualize, what are the different ways that linear equations can overlap? How can they relate to each other? So would it be possible to have exactly two solutions? And the word exactly is important because it might be possible to have two solutions or more, maybe infinite solutions, but exactly two. Let's think about that. So that example 2 on page 388, we have three different systems here. 2x minus 3y equals 2. We have x plus 2y equals 8. We have 4x plus 6y equals 12. We have 2x plus 3y equals negative 6. We have 2x minus 3y equals negative 6. And we have negative x plus 3 halves y equals 3. So now they give us these graphs. And each of these graphs is going to represent one of these systems, and we have to match, like which one represents which. So here we have 4 comma 2. It's not going to be perfect, but and then we have this graph here where the two lines are parallel. Okay? So which of these three systems will go with graph A? Or which of these three graphs goes with system A? That's the way they're organizing it. So remember, we're trying to explore how can things overlap. So these lines intersect at a single point in graph B. So at graph B, they intersect at one point, which is 4 comma 2. And a good way to do a sanity check is let me plug in 4 for x. What do I get? I get 8. And let me plug in 3 for y. 2 for y. I get 6. So that means 8 minus 6 is 2. So that's a true statement. So we've satisfied the first equation in that system. Okay. What about the second one? Well, if x is 4, then I have 4 plus 2 times 2, which is what y is, and that adds up to 8. So the second equation is satisfied. So that means this graph represents what's going on algebraically. There's two lines that intersect at this point, and this point satisfies. This is a point that's on both those lines, and that's what they're looking for. So that's one way that lines can overlap or interact with each other. They can intersect at one point. Graph B, system B, goes with graph C. The lines are parallel. And never intersect. So what that means is if I were to try to solve this, I would get something that doesn't make any sense. Maybe like 0 equals 1. And of course that's not true. So when you get something, when you try to solve a problem and you get something that doesn't make any sense, it means there's no solution. Or you did something wrong, but in this case we can know it means there's no solution. So a giveaway for that is if you look at this, equation 1, this equation is a multiple of equation 2. See, if I multiply, at least the left-hand side, I'm sorry, if I multiply the left-hand side by 2, I get the first equation. I'll get 2 times this is 4x, 2 times this is 6y. But I will not get that on the right-hand side. If I multiply this by 2, I won't get positive 12, I'll get negative 12. So what that means is that these two equations have the same slope, but they'll have a different y-intercept. So they're non-intersecting lines, and there's no solution. And then that leaves us with, this has to be graph A here, which if I multiply this equation by 2, the second one, I would get negative 2, sorry, I would get 2x minus 3y equals negative 6. So really, this equation, the second one, is really the first equation written a different way. And that's why you only see one line here, because there are two lines that are on top of each other, if you want to think of it that way. This system would have infinite solutions. Meaning that any point that I pick on this line would solve the first equation and would solve the second equation, because they're essentially the same equation written two different ways. But the point is that there's an infinite number of solutions. So we've answered our question. We can have zero solutions, like in graph C or in system B. We can have one solution, and that's kind of what we like when we have one solution. Oh, we solved for x, we got x is equal to something, I feel better about myself, and this is the answer. But these are legitimate answers as well. Having no solutions is an answer to the question or answer to the problem. So just because you didn't explicitly solve for x doesn't mean anything went wrong. But this is I guess what we kind of like to see more often, where you have one solution. Oops, one solution. So we can have zero solutions, one solution, or we can have infinite solutions. So this is C, B, or A. And this is nice because this provides us with a visual of what's going on. And it's nice to build up an intuition, which is part of the point of the course, is to have a library of functions like the square root function and the cubic function that we kind of can translate and move around and stretch as we see an algebraic expression. We can say, oh, okay, that kind of looks like this, and we can have a concept of what's going on. That's extremely important, and in fact, it's not healthy as you grow in math. It's not healthy just to be writing an equation and trying to solve for x and really not knowing exactly what's going on. That's not helpful. As you grow in math, and that's what I'm saying here, you realize that there's a healthy mix, I should say, between visualization or intuition and being able to write things algebraically, which is the kind of down and dirty, like solving for x, completing the square, the stuff that we don't like to do, but that needs to get done. There is a healthy mix between these, and usually you start out with an intuition and you draw a picture, and you know that skill is so helpful to develop. But when it comes down to it, if you really want to get a specific problem solved, you need an algebraic way of writing the symbols, and you need some operations that you've defined. And okay, I gotta square root this or factor this or whatever it is you got to do. The real way will solve. I think I said linear systems. is algebraically. And as we get to the reason that we have to eventually not depend too much on visualization or realize that it's just a tool to give us an idea of what's going on is because what happens if I have three dimensions? If I have, let's say, a system of three equations and three variables, like here. Oops. Like here. What if I tried to graph this? Well, what I'd graph is I'd have to graph three dimensions, which I can still kind of do, and I'd have to figure out how these planes are overlapping, and already it gets a little ugly to start drawing. If I just add one more variable, though, let's say x plus y plus z plus w, and add a w here, and then I need a fourth equation to really find a unique solution. How do I visualize that? We can't. We can't really visualize four dimensions. We can maybe have an intuition of what it might look like, but it's very difficult if it's even possible. 5, 6, 7, and beyond, we can only start to we can only kind of hope what that might look like, but we really can't visualize those higher dimensions. So we get an idea of what things look like from drawing them in 2 dimensions, maybe 3 dimensions, and then we realize, well, now we're going to develop an algebraic way of writing these things so we don't have to depend on pictures. And we just say, okay, if I move these symbols around, that's what this means, and these whatever 6-dimensional planes or whatever it is you might call them, they're overlapping this way, and you get a solution algebraically. Okay, that's enough talking. So that's the goal. Is we start out visualizing, we develop a good intuition, and we now we're going to develop a recipe of how we solve these things with symbols. And the first way is solving by substitution. Okay, and this is example 4, page 391, and they give us the equation x plus y equals 7, 2x plus 3y equals 18. This is equation 1, and this is equation 2. And I want to know where these lines overlapping without drawing the picture. So solving by substitution means I take one of the equations and I solve for one of the variables in that equation. So let me take equation 1. And from here, if I just subtract x from both sides, I can get y is equal to 7 minus x. Right? And I'll say plug into 2. Okay. So if I plug that into 2, then I get 2x plus 3, and what is y? Y is this. So 7 minus x equals 18. Well, let me distribute this, and already I can see, well, I have just x here. So that means I can solve the problem for x. So I do it. 2x plus 21 minus 3x equals 18. And then I just, combine like terms. I get negative x is equal to negative 3, so x is equal to 3. Okay, so I solved for x. Now what does y have to be? Well, y is 7 minus x, so 7 minus 3 equals 4. So I have y is equal to 4. So I have x and I have y. Or I have x and I have y. So that means I didn't even have to draw the picture. You see, it wasn't necessary. It's helpful and important, but not necessary. So now I know that whatever these two lines look like, I don't even know what they look like. I have my solution right here. That they're going to intersect at 3, 4. Right. So, this is the same problem we just did. We're just solving it a different way. Yeah, this is a problem we did with the tickets. So, and then there's going to be, as we add in variables and equations, let's say I have z plus x plus y equals 2, 3z minus 4y plus x equals 6, and 6z plus 2y minus x equals 1. Let's say I have this system here. We'll start to call systems of equations their own they develop a nature of their own, and they're called matrices or linear operators. And we'll just write the coefficients: 1, 1, 1, 3, -4, 1, 6, 2, -1, and then we would kind of draw a dotted line here: 2, 6, 1. So you organize what's important, and now you have this matrix here called an augmented matrix. This is a 3 by 3, and you do this stuff called Gauss-Jordan elimination, and you'll find what x, y, and z have to be in order for all these three things to be true at the same time. Really, what will happen way down the road, if we can really get into this is some matrix that I'll call A, and this is what we'll call a vector B, and these three things are some unknown vector, which we'll call x equals, and I write x, y, z. It's a vector of three coordinates, and we want to solve ax equals b. So this is a linear operator times a vector equals another vector. But this is known. This is 2, 6, 1. That's what b is. It's a not a point. It's a vector, but this is the new stuff. This is these things, these matrices develop a nature of their own, an algebra of their own, where you can kind of have an inverse matrix. You can multiply both sides and solve for x and do stuff like that. So that's what we'll eventually get into. For now, that's pretty much going to take you through section 5.1. I'll just do number 3 and number 7 and write the homework, and then you can be on your merry way, get started doing it. So number 3 on page 397 says 2x minus y equals 8, 3x plus 2y equals -3, and they want us to match these equations. They have a, B, C, D here. They have 4 different equations on the previous page, and which one goes with it. Well, these two lines are definitely not parallel. Yeah, they're not parallel. So that means it has to be either A or D. And I'm just going to go to the back because I don't feel like working it out. So that's not a good habit. So do as I say, not as I do. So 5.1. Number 3 is D. Okay. So D looks like this. It's actually 4. They have all 4 in there. And they have a line going like this. You got a line going like this. Ugh. I didn't even draw it well, but they intersect in the 4th quadrant. And that point that they intersect at is 1, -3. So that means if I plug in 1 and -3, wait, what? One -3. Did I write that wrong? Oh, this is a 5, that's why. Okay, if I plug in 1, -3, then I'll get 2 minus -3 is equal to 5, so that's true. And then 3 minus 6, because it's -3, will equal -3, so that's true. So that point solves it. It's just doing the example that we did before again. And then number 7, they want you to solve it by graphing. So we have 3x minus 2y equals 12, 7x plus 2y equals 8. So let's graph this. When y equals 0, x has to be 4. When x is equal to 0, y has to be -6. Whoops. When y equals 0, x has to be 4. And then this is -6. So this is this line right here for the first one. The second one, when x is 0, y is 4. When y is 0, x is 8 over 7, which is just bigger than 1, so it's right around here. So what you would do is you'd graph these two, and you do it on graphing paper, and you'd say, okay, they intersect right there. Whatever point that is, it's maybe around 2 comma -1 or something, just like we did before. It'd be good to just even do it on your graphing calculator when numbers get a little bit ugly. So that's the homework. Will be numbers 2 through 16, and let's say every other even. No, let's say evens, because that's 8 problems. That's not that big a deal. So there you go. Have fun.